In practice, we often do not deal with a single moving charge. We sometimes do, but we do not always do that. Rather, we often deal with a current, a charge carrying current in a wire. A current, as you know, is made of a whole bunch of moving charges, right? And if you expose that current to a magnetic field, then you'll find that every one of these moving charges will now be experiencing a magnetic force, right? A magnetic force. So as a result, there will be a force on the entire current. So let us calculate how to find the magnetic force on an entire segment of charge carrying wire. Right? Force on a current segment. Now you notice I said a segment, not an infinitely long current. Because if the current is very, very long, they got infinite number of moving charges, right? And each charge will experience a force, so the total force could go to infinity. So that is not what we want to know. So let's isolate a little segment out, okay? From here to there, this segment contains a number of moving charges, and the length of this segment, we give it a length from here to there, okay? And we are going to call it ds, okay? Okay, we're going to call it, actually, no, the first thing we're going to do is we're going to call it L. Okay, that's the length, we're going to call it L. Later on, we're going to make it smaller, so we call it ds later. We call it L. Now, again, the reason why this segment of wire will be subject to a magnetic force if you put a current through it and expose it to a magnetic field is because this segment contains a whole bunch of moving charges, and each charge will be subject to a magnetic force. So the idea is, let us figure out first the charge, the force experienced by one of these charges. Okay? Then I sum over all the forces on all of these moving charges. Now, you notice that we only need to consider the drifting velocity. That is the velocity of these charge carriers responsible for producing a current. We're not going to be dealing with random velocity, even though each particle moves randomly, in addition to the drifting velocity. Why? Because the random motion, being random, it's got arbitrary directions. Okay, so you know the forces exerted on each charge carrier due to its random motion will have random directions. So therefore, it's going to add up to 0. Okay, so therefore we're going to only consider the drifting velocity, which is responsible for the current. Okay, so each of them, on average, moves with a drift velocity vd. Okay, so let me calculate that. Let me find the magnetic force on this one single moving charge q. Okay, moving with a drifting velocity vd. So I have q vd cross b. Isn't that the magnetic force on this one single moving charge? Okay, one single moving charge. Now, what is the magnetic force on the entire current segment? I have to sum over all the moving charges. Okay, all the moving charges within this segment. That will give me the magnetic force, right? Now, I'm going to do something here. This is q sub I, and here's vd sub I. This is the drifting velocity of the ith moving charge within the segment. But b is the same, assuming b is the same, okay? It's uniform. And I'm going to therefore isolate the summation out from the b field. Okay. Now, take a good look at this. Q, V, and the sum. What does that remind us? Okay, what does that remind us? Do you recall when we calculate the current, okay, when we define, first of all, we define the current as dq over dt, right? And then we express current in terms of the drifting velocity and the charges of the charge carrier. Remember how we did that? That was way back in chapter 26. Actually, 27, okay? In chapter 27. You recall that formula? Okay? If you don't recall, it's okay. We're gonna pick it up again. And it says, okay, let's actually work it out together to refresh your memory. Okay. You know, if I want to calculate the current, okay, this area here is A, this area here is A. If I want to calculate the current, I must count all the charges passing through this window, right, per unit time, and all these charges, in order to make its way from through this window over time dt, they must live in a certain cylinder, and that cylinder should have a height of Vd times dt. Recall that argument? Okay, and it's also got a cross-section area A, and therefore we know the volume. The volume of the cylinder would be cross-section area A times Vd dt. So A Vd dt. That is the volume. Okay, the volume times what? Times the number density. How many moving charges are there per unit volume? M. That will give us the total amount of charge going through. It will be dq. And you divide this by what? Actually, sorry, before I do that, that will be just the total number of moving charges multiplied by the charge carried by each one of them. That is the total amount of charge passing through this cross section over time dt. And you divide it by et. By definition, you get a current. Okay, I. So I is QNAVD. Okay, QNAVD. Let us see how that is related to our case. Okay. I is a scalar, however, the current density J is a vector. The current density J, which is I over A in magnitude, would be Q times N times Vd. Okay, Q times N times Vd. That is a vector. Now, when we measure the magnetic force, we want to express in terms of the current because that's something really easy to measure. We don't want to measure it in terms of the current density or even worse, the drifting velocity, because these things are not easy to measure. So we want to rewrite it in terms of the current, I, flowing in the circuit. So let's see how we can rewrite this expression in terms of the current. Okay, take a good look. What is this expression, really? Let me rewrite this expression. Okay, what is this? What this is? It's a sum of Q times Vd for all the charges within this volume, right? Within this volume. Now, we know the number of charge carriers per unit volume is m. So how many charges are there within this region? How many charge carriers are there within this region? That would be n times the volume of this region, right? N times the volume of this region, and each one of them will contribute one term to this sum. Okay, so this sum really is just equal to the number of charge carriers times in this region times Q times Vd, right? And the number of charge carriers in this region, once again, is n times the volume of this region, which is n times L times A, okay? And then times Q. Let's assume Qi is the same, so every charge carrier has the same charge Q. Vd, let's assume they're also the same for everybody, for all the charge carriers. Cross B, right? And now, let's try to compare these. Okay, let's try to compare these. Again, I don't want to deal with a vector Vd because that has to do with the direction of the microscopic particles moving from place to place, which I cannot measure directly. What I do know, however, is that Vd, assuming it's a positive charge, will flow along the wire, right? Flow along the wire. And if it flows along the wire, doesn't it flow from here to there? Now, if I define a vector pointing from here to there along the direction of the wire, doesn't that take care of the direction? So what I'm going to do is I'm going to define a vector L. Okay, L is no longer just a scalar. It's not a scalar anymore. It's a vector. It has the length from here to there, but it points along the direction of the wire, assuming that y is straight. If it's not, I'm going to just break it down to infinitesimal segments, and each segment called ds. That is straight. So here's L. It flows. It points along the direction of the current flow. Obviously, this vector L and the vector Vd would be pointing in the same direction. Therefore, I can transport. Okay, I can transport the vector sign from Vd to L. Okay, that's a key step here. So I'm going to write n Vd. I'm going to move Vd to here. I'm going to keep A and I'm going to keep Q. I'm going to move L over there, making it a vector cross B. All right. You see, I transported this vector sign from here to there, but that doesn't change the direction at all. Why is this a good idea? Because take a good look at what do I get here. NVDAQ. What is that? NVD. Okay. NVDAQ. Isn't that the current? this is nothing but the current. Okay, so now I'm able to rewrite the expression for the magnetic force on this segment as I L cross B. Okay, a handy formula to know. If you're not given a single point charge moving with a velocity v, rather you're given a segment of the wire carrying the current I, the magnetic force exerted on this wire when you expose it to an external B field is IL cross B. L is again a vector whose length is the length of the wire segment and whose direction is along the direction of the current flow. Now, if the current flows in a curved wire, then L, I have to be careful about it because I'm assuming here it's a straight wire. It may not be a straight wire anymore, and so you have a segment like this. Okay, and you have a wire like this, and so what I'm going to do now is I'm going to define an infinitesimal value of L. In other words, dl. In fact, the text will call it ds. It's the same thing. Okay, what is the magnetic force on this little segment? That would be df, right? df equals what? I ds cross B. Okay? Be careful about that. ds cross B. It's the same I. No matter how short the segment is, the current through the entire wire is always the same, is I. Okay, given that, can we find the total magnetic force on the current loop? What's a loop? Okay, it's something that returns back to itself. It's self-enclosed, a current loop. Okay, this is the force on a segment of the loop, ds. In order to find the total force on the entire loop, I would have to do this. I have to integrate over df. Okay, I ds cross B. And since the loop returns to itself, it's a self-enclosed path, I'm going to use this symbol to indicate that. Right, over the entire loop L. Now, if the magnetic force, the magnetic field is uniform, okay, if the magnetic field is uniform, which is often the case, then let's see how we might simplify this. It's uniform, therefore I'm going to take it out of the integration. It doesn't change from place to place, and the current I is always the same. I can always take that out, so that would be I and then integral ds over the loop, and then cross B. This B is now out of the integral sign. In fact, I can isolate this integral like this. Alright, tell me, what do you think this is equal to? You're adding vectorially all the segments up. You're just finding the net vector movement as you go along the loop, and that of course is 0. For any loop, it's 0, so you get 0. Okay, what does that tell you? It tells you the net magnetic force on an arbitrarily shaped current loop is always equal to 0 as long as the magnetic field throughout this loop is uniform. Okay, in other words, you cannot exert a net force on a current loop with a uniform magnetic field. Does that mean the force cannot do anything to the loop? Well, there's no net force on it. Does that mean the magnetic field cannot do anything? Well, it turns out you can do something, but what you can do is not to exert a force, but rather to exert a torque. Okay, and we're going to investigate that a little later. But now that we're talking about how to calculate the magnetic force on a current, let's take a look at an example first. It's also from the textbook.